Okay, I am going to talk about microscopy. Why do we need a microscope? That is because we are not able to see many small objects. One needs a microscope. Now, to imagine this, let's look at what does microscopy do. Basically, we think that cells are very small, so we can't see. So one could argue we can keep on magnifying the image and we should be able to see the cells, but that doesn't happen because microscope provides one more important function. One is what we call the magnification, that it makes the object larger, but more important function is the resolution, that is how small objects can be distinguished. To take an example, let's say we are in a field and looking at trees at distance. Now, when we look at the trees, we can see the green foliage and the stem and so on, but can we see individual leaves? As we get closer, we begin to see small leaves. Why? Because now the image that is found on our retina is coming from smaller areas, and therefore our retina can resolve it. And similar thing is microscope doing, that it looks at smaller and smaller field of view, and thereby let us see it in a better way. And that's what we use the term resolution. An optical microscope, which is based on the visible light range, I'll explain the formula, can let us resolve at the best objects which are separated by 200 nanometer distance. If they are closer than 200 nanometer, we will not see them as distinct object, and that's what we call resolution. Electron microscope, on the other hand, can resolve less than 0.1 nanometer, or now even atomic level resolution is possible. And that's where many times in biology also one wants to see electron microscope to look at structures. But I'll be talking today only about light microscopes, different versions of light microscope. As I said, there are a large variety of microscope, conventional Brightfield microscope. Then we have variants of light microscope with contrast enhancement systems like phase contrast, polarizing, Darkfield, differential interference contrast. I'll talk briefly about these. Then fluorescence microscope, more advanced version of fluorescence microscope is the confocal microscope, which has become a basic tool in cell biological studies today. Everything one can do with confocal, which I'm not going to talk today. And then of course there are transmission and scanning electron microscopes, combinations of confocal and electron microscope. Now there is a system where you can examine the same object in three-dimensional arrays by confocal microscopy and then by electron microscope, transmission electron microscope or scanning electron microscope. There are combinations of that have been developed. And then there are various kinds of atomic force and other tunneling microscopes which provide more surface features of an object. Now, microscopy, as I said, serves two functions. One is image size to object size ratio. That means object may be small, image becomes larger, that's magnification. Resolution is the fineness of detail that can be distinguished. Now, historically, we know microscope was first made by Antoine van Leeuwenhoek, who was a kind of illiterate person, but then started doing experiments with this, and he became one of the best microscopists and a very good biologist at that point. And this was a very simple device, this microscope, and he made hundreds of such microscopes by hand. There was no factory making it, but this would provide up to 60 to 70 times magnification of the object. But then gradually other kinds of microscope came in. Historically, remember, microscopes were objects of beauty as well. So they will be gold plated, they will carry various kinds of designs on their surface, a very nice looking box. That was part of not just utility but also a kind of aesthetic sense. So the historical microscope, for example, these kinds of tripod microscope is characteristic of those microscopes manufactured in England. Whereas in Italy, which was another place where microscopes were manufactured, they would go by more conventional design, having a very expensive body made up of various designs and so on. And then already we see by 1630 people had looked at various insects to magnify them, look at the various objects. And of course, the cell was discovered because of microscopy. Now, how does a microscope work? A basic compound microscope, it's called compound because it has two lenses, one objective lens and a eyepiece lens, where eyepiece lens remains near the eyepiece, objective lens near the object. So a typical simple compound microscope, let's say this is where we place the object on a slide, light comes through the object, that's why we call it transmitted microscopy, and then this is the objective lens which magnifies, forms an intermediate image, and that intermediate image is now focused by the eyepiece lens and magnifies it. and as a result of this combination of two lenses magnifying an image, we see an inverted virtual image. We can't project it. In a typical microscope, we can't project it. So if you want to take a picture, we need a different optical system, some modification of this eyepiece type, so that we can see a real image. And this is what, for example, a microscope like this, which must be expensive because it looks like gold plated or made of brass. That's what it used to be. Which were the microscopes which were actually available. The only addition will be that they will have a third lens which we call oil immersion lens. I will talk about that. But typically we have low power, high power microscope, which I am sure many of you would have used in schools, where you have a low power objective and a high power objective and you see through the microscope. That is a simple compound microscope. And remember, I will explain later on, some great discoveries were made by microscope this kind, simple microscope, not very sophisticated microscope that we are used to now. Now this is what a modern day research microscope looks like. If you look at the anatomy inside what it has, it's a very much more complicated than what simple microscope used to be. But principle is remain same. That is, we have a light source, there are two sets of diaphragms. One we call field diaphragm, an iris diaphragm which can be close to very small pinhole or open large, and similarly in the condenser there is a condenser diaphragm or substrate diaphragm which can also be closed or open. Then there is a condenser lens which will ensure that the light source which is coming as parallel beam of light gets focused on the object, and this is an important point in microscopy. And then over this we have our object here, and then we have the objective lens which will make an intermediate primary image which the eyepiece focuses and lets us see that. Now in a microscope what happens is there are a lot of electronic control to make many things automated. Light system, instead of manually controlling, you can control it by a switch in a more smooth manner. So this microscope we call upright microscope, which is the more conventional one. There is a version of this inverted microscope where the objectives are on bottom, light comes from the top, but you see it same way. Maybe somewhere I will have a slide to show that. So this microscope has a typical visible light source here. Light comes from here through a series of lenses and filters so that you can change the wavelength of light as you want to enhance contrast. And then there is a mirror here, which will reflect the light up, so that now it comes to the condenser, and condenser will focus the light on the object here. Objectives are in place, and then light can go, and there is a set of prisms so that either light can go to your eyes or it can be sent to a camera depending on what kind of camera you have. The same microscope can also function as a fluorescence microscope. For fluorescence we need a different light source, typically a mercury lamp, which provides very intense light of complete wavelength from UV to infrared, and that's why we use mercury lamp. This light comes again through a series of lenses, and here is a dichroic mirror which will reflect the light down, cause fluorescence. I will explain that later, what is the principle of fluorescence. And then light gets reflected back, and this dichroic mirror now allows only a certain wavelength to pass through, which we can see either through our eyepiece or it can be deflected to the camera. This is typical, and many functions get automated, and therefore they become extremely complicated system to look at, but basic things remain same. And remember these two things, substrate diaphragm in the condenser and field diaphragm just above the light source. These are two very important things which must be adjusted properly to make sure that your microscope provides you the best possible image. Now this picture shows what is magnification, purpose of magnification and versus resolution. These are my favorite material, polyethylene chromosomes. For example, this same nucleus we can see with 10x, we will see a very small image, but if we magnify it, we will look at like this, very blurred. One will say it's out of focus, no good. Same image photographed with the 20x objectives, but magnified to same time gives you slightly better. 40x again magnified to the same level, you get still better. 100x wall immersion, you get the best result. And this differentiate that it's not the magnification which is important, it is the resolution. And how does resolution work? Let's say this is again showing same thing, original magnification. These are at magnification as they are. With a 10x objective, we will see a much larger field of view, we use 20x, we get much smaller. For example, now we will see only this much field. When we change it to 40x, we now begin to see only this smaller field. If we use oil objective, our field of view becomes much smaller, but better resolve, because now we are looking at a very small area and magnifying it much more, and that's what resolution does. Now, to understand resolution, let's look at, this is what a scientist called Airy described the principle of resolution, that if you let a light pass through a pinhole, then light doesn't come out as a single circle. It comes as a single circle of bright light, but then surrounded by less bright spheres, and these were called as Airy disks because he described them. Now, the purpose of this Airy disk is, for example, if you look at this pinhole, light is coming from this pinhole, but its image is not just this circle pinhole. It is surrounded by these less bright rings. Now, what happens is, if let's say you have two pinholes very close by from which light comes in, but if the pinhole points are specially separated, you see them as 2 points. But if they are overlapping, your eyes will tell you only one object. You can't resolve them. And this is the most important principle that determines microscopy, and which we must understand. The Airy disk and the diffraction that happens because of the edges from which the light refracts, and it gives a differential distribution. This property is now being used also in confocal microscopy to provide you super resolution. That if we can eliminate these fringes of lights, we will get a much sharper image. This was a simple thing that we use now in deconvolution. And this is, for example, an object, a real life object, from light is coming from each point in a cell and is getting refracted, and we see an image. But now what we can see is some points are far away, so they are resolved, but they are just at the border of resolution. We can still see, okay, there are two possible small things, but then if they are too close by, then we can't see them. These two are too close, we can't see them. And this is where the limit of resolution has to be understood. And this limit of resolution microscope can be attained only if you adjust the microscope in a proper way. And that's where this Abbe's formula of calculating limit of resolution comes in, lambda by into 0.61, which is a constant, divided by n sin alpha. N is the refractive index of the medium through which light is passing. It can be air, it can be water, it can be glycerol, it can be oil, glass accordingly, and multiplied by sin theta. Sin theta is the angle of light cone which is going through the object, and this I'll explain how it's done. Now, for example, if you have a low power objective, the NA is smaller, numerical aperture is smaller, and therefore focal spot is bigger and you get less resolution. As the numerical aperture becomes larger, your focal spot thickness becomes less, and therefore you can resolve between different objects. That's what the low power, high power and the oil objective or better resolved objectives provide for. Now, we say oil objective gives us better resolution, but oil objects let us look at a much smaller area depending upon higher magnification. How does oil help in resolving it better? Oil, two things are there. The oil objective is close to this slide, it's touching this slide, and therefore its angle, you see, if you have a cone, if you are closer to the base of the cone, you are covering much less area. If you are away from the cone, you cover much wider area. And in this case, the cone is inverted because light is coming to the object and then crossing and becoming the inverted cone. And therefore, if you are closer, you cover much larger area than when you are at the top. And 10x, 40x objectives are slightly away from the object. 100x objective or immersion objectives are touching the object, and therefore they cover a larger area, and therefore the sin theta value of the angle of incidence becomes greater. And n is the refractive index. If you are using air, let's say refractive index is one value, water has a high refractive index, immersion oil has still high refractive index, and therefore in the formula lambda 0.61a by n sin theta, if the denominator becomes larger, your numerical aperture becomes small, the limit of resolution becomes smaller, and that's what we achieve by using immersion objectives, by getting close to the object. You see, just as in this case, what happens is the object is far, many of the light rays that are coming are outside the field of view and therefore they are not covered. But when you are using an oil objective, all these light rays are captured by the oil objective and therefore you get a much better resolved image. Now, but the important point in microscopy is adjustment of illumination. That's the most critical point, but I must say unfortunately most often ignored point. You just see some light and begin to see an object and you see magnify and you feel happy, but you are really not getting the kind of image that you want to do that, and that requires, one of the system is Koehler illumination, which require these following steps. Step 1 is, for example, this I have drawn here this lower part of the microscope to illustrate what are the points that we need to control. So first is turn on the illumination wherever the illumination switch is. For example, here the illumination switch you turn on, put a slide on the microscope, use a low power objective, focus the objective by moving the condenser up and down. I am sorry, the stage or the objective up and down, and then comes the more critical components. The more critical components, you close down the field diaphragm completely so that you are letting in light only through a pinhole. And then move this condenser knob number 3 in the figure here up and down till you get, you see this is the closed diaphragm but image is not sharp. By moving the condenser up and down you are making this image sharper, but then it will not automatically come to the center. You will need to use the centering screws which are located on both sides of the condenser, clockwise, anti-clockwise, to ensure that this comes in the center of the field of view. You are not seeing the whole of entire field, you are seeing only one small area, but that must be in the center. Now next step comes is opening this field diaphragm. You start opening it, make sure that it remains concentric with the field, total field of view that you can see, and then if it is slightly eccentric, again use these condenser knobs, centering knobs to adjust it, and then just open this diaphragm control enough to eliminate the field of view, not more than that, because if you open it more you are letting in extra light go in the microscope and thereby create glare. So that is first thing. This is the first part of Koehler illumination, of making sure that your light is uniform, light is centered and is making a pinhole on the object so that you get the appropriate cone coming up. The next thing is the substrate diaphragm control. Substrate diaphragm again can be opened, can be closed. If you have it full open, you will not see good contrast. You will see slightly glare on the image. Optimal control, yes, you see good contrast, no glare. Close it too much, the image becomes dimmer. Now it depends on what kind of image you want. You can vary the substrate diaphragm from this level to this level, but typically it is about 2/3 of the maximum diameter that the substrate diaphragm can open. That's what you do, and then get the best contrast. But sometimes for certain contrast you may have to reduce it, you may have to open it, but that will vary with the object that you want to examine. The objectives are not simple lenses anymore. Unlike Leeuwenhoek, who had just one convex lens here and another convex lens there, now the objectives are very complex. The reason being that in the optical microscope we have two major aberrations. One is called the spherical aberration, that is chromatic aberration. Spherical aberration, because it is a convex lens, although there is a point of focus, but then the image will appear curved instead of straight. Our eyes can continuously look at things which are far and away because you have accommodation. Our lens is soft, but glass being a hard lens, it will focus on only at one point, and if the image is curved like this, it will focus either here or here. So a simple microscope, the ones which are less expensive, when they give an image, you will see either you focus on center, periphery is out of focus. You focus on periphery, center is out of focus, and that's what spherical aberration is. And that correction is made by a combination of lenses so that you get a planned field of view. That's called plan objective. Chromatic aberration comes because of the different focal points for different wavelengths. Red, green, blue, three major components of visible light, do not focus at the same point. They focus at different distances. So if you look at colored object, you will see red is at one sharp, green is not sharp, or blue is not sharp, and that's chromatic aberration. And that is corrected again by lenses called achromatic, which are a combination of lenses made of different qualities of glass with different thicknesses and so on, so that all the three wavelengths, at least simple chromatic, red and green are focused at the same point, blue is slightly out of focus. More advanced version of the chromatic aberration is apochromatic lenses. But obviously that requires more and more lenses in the train of lenses. You see, an 10x apochromat already has these 9 or 10 lenses, very precisely positioned at each other. If you disturb any one of them, your object is gone. You can't do it, and that's why one has to be extremely careful. And then there is another correction required, cover glass correction. You see, typically we use cover glasses which are 0.17 millimeter thick, but they can be thicker, they may be thinner, and especially when one is using culture medium, the object may be on a petri dish or on a cover, and you need different thicknesses. So many objectives come with a cover glass thickness adjustment, so that you can rotate a knob here. This knob can be rotated and you can adjust the cover glass thickness from 0.13 millimeter to 0.2 millimeter. And this is available in several objectives. We have in our lab also, which have some of these functions where you can adjust the cover slip thickness. And then these are apochromat objects. Again, apochromat object, plan apochromat are the best. An apochromat object may have spherical aberration. Plan apochromat will not have spherical or chromatic aberration. And obviously they are extremely expensive. I can just tell you that at 63x apochromat object, oil immersion object, plan apochromat can cost more than 1 lakh rupees. And so be extremely careful about these, that if they are damaged, they can't be repaired. These are not something that, okay, you can get it repaired or it's just to be thrown. And that's what, and partly because these are very precisely crafted, made in a precise manner. I mean, imagine if 0.1 micrometer difference between these two lenses and that's gone. They have a special cemented between them, and so they have to be extremely carefully handled. Now then comes the next kind of microscope called Darkfield microscope. You see, what we talked so far was Brightfield, where the field is bright, objects appear darker. Why they are darker? Because we give them color and therefore they absorb certain wavelengths, they let certain wavelengths out, and therefore we can see the contrast. Darkfield microscopy is useful when you have objects of very high refractive indices in the field of view. That allows you to see them by diffraction and refraction. Now what we do for this is, in the condenser, the central part of the condenser blocked light. So you no light comes from the center. Light comes only as a ring of light, a hollow cone of light, which focuses. But this hollow cone angle is such that when this crosses into the slide, the light rays go out of objective and therefore you don't see anything in the object. What you see in the object, if there is an object of high refractive index, is because of the high refractive index, it will diffract or refract the light, and therefore some of the light rays will change the direction and enter the objective. So you will see a dark background and bright objects. This is the whole principle of it, that you see in a typical microscope you see the whole of this light going in, but in a dark field microscope we put a stop here in the center. So no light goes from here, instead light goes only from periphery. But that light normally will not enter the objective because it's an angle which which is beyond the field of view of the objective. But if the object has some bright, some refractive index object, high refractive index, then they will refract or diffract the light that will enter the object, and you will see an image. For example, this is a bright field image of a diatom, and this is a dark field image of the diatom. And you see it's completely dark, each appears as a, if you look at that, one beautiful side but a very ugly side for microscopy says, if you take an unclean slide which has some dust particles, put it on a dark field microscope, you will see like starlit night sky. Each dust particle is refracting light, and this disturbs microscopists. And therefore we need absolutely clean things so that there is no unwanted image forming objects coming in the field of view. Now then we can have different kinds of dark field imaging. For example, this is a radiolarian, bright field, these are dark field imaging. You can put a red filter, you can see red color, blue filter, blue color, or we can see when a tick, it looks like fluorescent, but it's really not, nothing, just live tick, put on a dark field and you see the cuticle refracts the light, and we can see that. That's what we typically see, the embryonic cuticles in Drosophila larva. They are high refractive index and therefore they appear bright. Or a planarium or something else, they look very colorful, but against a dark background. Then we come to the next very important development that happened in microscope was the phase-contrast microscopy. Live cells we cannot see in a microscope. Reason being that any image formation requires contrast between adjacent points. To appreciate contrast, let's again imagine that in the night we see stars and moon. Okay, with pollution we may not see it, but if it's a clear sky, if they are not street lights, we see very bright stars and so on. Where do the stars go in day? They are not hiding away somewhere, but because there is so much of light of sun that you don't see them, because the contrast between the light coming from star is compared to the light of the sun is much poor, and therefore you don't see them. And this, if we can change this contrast, then we can see this, and that's what phase contrast does. For example, these are cells in culture seen with an ordinary microscope. Just light microscope, you do the best adjustment, all that you will see is very faint images of the cell. You will find, okay, there is something here, but what it is you can't make it out. Same field, when looked at phase contrast, we can see real things. So phase contrast microscope becomes very critical for looking at live cells. And actually phase contrast microscope discovery by Jernicke won a Nobel Prize for discovering the principle of phase contrast and then making use of it in phase contrast microscopy. How does it work? It again depends on certain basic optical principles. That light waves coming from a source, there is not just one light ray, there are millions of light waves coming in. Now they all travel with same wavelength, and if they start at one point, then they all will travel like waves in synchrony. See, just as you have waves in water in synchrony, but then if another light ray is coming which is slowly moving or which has been retarded with reference to the other, how can light ray be retarded? If you let a light ray pass through a denser object, an object of higher refractive index, obviously its velocity will get reduced. And therefore, if you have, let's say, an object here, light rays come from here and some light rays are passing by. When they emerge on this side, these light rays have arrived earlier than these ones, and that's how you see this object differently. Otherwise, it's all transparent. And phase contrast microscope takes advantage of this difference in the arrival of these light waves because of interference, because these light rays which are passed through the denser object and light rays that are passed through the lighter object, they will interfere and give you an image. And this interference principle is this, that for example here 3 color lights, red, green. Now red and green are not moving at same time, but they are in phase because they have same amplitude, but more than amplitude is their wavelengths are same. The distance between 2 peaks or 2 troughs is identical, and therefore we say that these light rays are in phase. But if one of them becomes slower, then peak and trough of the two do not become synchronous, and then they will begin to show an interference, and that can be destructive interference, constructive interference. Constructive interference, when they are in phase, if you have one light ray, you have another light ray, the amplitude increases and you see brighter light. But if you have one light ray and the another light ray is out of phase, they tend to annihilate each other, nullify each other, and in the process you see a darker area. And this is what happens so in a cell we have objects of different refractive indices, and therefore light rays will be retarded, enhanced in different areas, but the difference between them that happens is much smaller. For our eyes to detect the interference, we need at least lambda by 4 retardation or enhancement. If the retardation enhancement is much smaller, for example in this case lambda by 20, our eyes will not detect it, and which is what happens in a real cell, unstained live cell, that the refractive index difference between the different components is so small that retardation is less than lambda by 20, and therefore we don't see it. What phase contrast does, it enhances whatever, let's say lambda by 20 plus lambda by 4. Lambda by 4 is introduced by hardware component of the phase contrast microscope. What phase contrast microscope has is, in the condenser it has an annulus, so that light will come out through this white area only as a hollow cone of light, and if it is unrefracted, it will pass through this dark area, in the objective, and it will not be allowed. Which light ray will be allowed? If light rays coming from here are refracted by some object, they change the direction and they then tend to enter through outside this faceplate area, and therefore these and the direct light rays that come in unrefracted, they interfere and generate an image. And that is what happens in this case in the phase-contrast microscope. What we do is we have this condenser annulus here below the condenser, and objectives are special. Each objective you can't use for phase as a phase objective. It has to have that specific annulus, and annulus is specific for each objective. Both faceplate annulus and the phase annulus, they have to be specific for each objective. So we can't use just one phase annulus for 10x and 20x and 40x and 100x objective. Each objective will have to have its own built-in annulus. So we get that objective. And the point is that once you put them concentric one over the other, we get the image. As you can see from this image here, the bright circle is the phase annulus through which light is coming, and the dark circle is the phase plate in the objective. If the two are not concentric, then your whole purpose of phase retardation is lost, and you get an image which is slightly better but very hazy. You try to adjust them more, same thing. Only when they become completely concentric, like a magic, you see the real image. Now how do you do this? In the phase condenser, in earlier models there were centering screws for phase plate. Just as we are condenser centering, there will be additional centering screws by which you can adjust this phase annulus in the objective, in the condenser one way or the other. Nowadays they are much better mechanically organized, so that these phase annuli are always will come in position when you change the condenser turret. But still sometimes we need to adjust this, and if that is not done, you will say you are examining the phase, but you get this kind of image rather than this kind of image. So phase contrast microscopy has become extremely useful in 1940s, 50s when this became available. That was the first time that movies of live cells could be made. Earlier times, live cell could not be photographed because you can't see it. You can stain it, but once you stain it, you are looking at a cell at a fixed moment of time. You are not looking at what was before and what will come after. And that's where phase contrast became very critical in understanding dynamics of things in a live cell. And this is there's two versions of phase contrast microscope. Most common is positive phase contrast. There's another version which is called negative phase contrast, which gives you just reverse image. The basic point is that in positive phase contrast, the phase plate introduces additional λ/4 retardation. In a negative phase contrast microscopy, the phase plate will enhance the unrefracted light by λ/4. It will move faster, because the other light which is refracted and therefore deviant will move slower because of additional refractive index provided in the phase plate, and therefore the image has become, like you see, the positive versus negative image completely reversed. But most common is the positive phase contrast, that is most commonly utilized almost everywhere. Then there is an advanced version of phase contrast, that is differential interference contrast, or DIC. This has become very popular in recent times, particularly with confocal microscopy, because unlike phase contrast, DIC can also be focused at each object plane, and therefore wherever you are focusing you get a sharp image, unlike normal microscopy. But it requires a series of multiple components in this. Basically it depends on polarizing the light. What is polarizing? When a light is coming from any light source, light travels in a straight direction, all right, but it has oscillation of waves in 360 degrees. Some waves are oscillating in this, some are oscillating in this, and they are all angles, and this is what we call as unpolarized light. Any light that we see normally is unpolarized. A polarizer is a special device, a glass, which will ensure that light rays oscillating in one particular direction only can pass through. All of these are blocked. So for example, this cartoon here shows the yellow and blue are same light but oscillating in different directions. Once they pass through the polarizer, the blue plane polarized light are obstructed and you get a polarized light. So now what happens when this light falls on molecules which are oriented in different directions? They'll make images differently, and that's where what we call birefringence or polarized microscopy takes advantage of molecular organization of components in a cell. Each cell has different components, have different kind of molecules, and they are in different planes, and therefore when light passes through these molecules, it has a different effect, and that's what the DIC takes advantage of it. But what it does is, so first of all, it will have normal light source, a polarizer in the object. For example, this is where the base is where you have polarizer. Then in the condenser, there is a special prism, Wollaston prism, which will split the light into two different directions, and then it illuminates the object. So what it does is, you have polarized light, now you make it two places. Half of them are polarizing in one direction, half are at 90 degree to that, they are oscillating. They pass through the object and they get diffracted and the polarization changes. Now these light rays are collected by another prism in the objective, Wollaston prism, which will try to combine them, make their interference, and then make an image. And that image is finally allowed us to be seen by us through an analyzer, which is at the top of the objectives. We slide in or slide out, that's the analyzer. Unless all these four components are in proper optical alignment, you don't see a DIC image. And so, but DIC image making is very convenient to look at things, and that's where it has become very popular now, because again you can see unstained objects, you can see live objects, you don't need to provide them a stain or kill them. Now this picture compares the different kinds of microscopy, what kind of images we get. For example, this is a Brightfield unstained. You can just see a metaphase, okay, there is something there. You see in polarized light, you begin to see a better, because the spindle now forms, because the microtubules are arranged in different directions, they give birefringence, and therefore they will appear darker while chromosomes appear brighter. The C is in DIC image. DIC image gives you a three-dimensional effect, a pseudo three-dimensional effect, because depending upon the degree of refraction and interference that provides, it gives you some areas brighter, some areas shaded, and therefore you begin to feel that the three-dimensional image. Phase contrast lets you see more, objects are darker. This is of course electron microscopy, we get much better view, much more resolve, and this is what people, when they didn't have all this facility, would do it, draw it. And I'll show you later on an example how drawings can be much more meaningful than what we photograph. Because photography doesn't allow us to see everything that our eyes can see. Then we come to the next point, that is fluorescence microscope, which has become very common because it allows us to look at specific molecules in a cell. And of course, before fluorescence became available, cytologists had developed what we call cytochemistry or histochemistry, whereby again one could localize specific classes of molecules by their specific staining properties or their reaction with specific stains. But fluorescence has become very important in microscopy today, and this is what led to the development of confocal microscope, the phenomenon of fluorescence. What is phenomenon of fluorescence? Fluorescence is that every atom has electrons in different orbits because of the different energy levels. What fluorescence does is that certain molecules have this property, that a particular quantum of energy received as a certain wavelength, one of the electrons gets more energized and therefore jumps to higher orbit and becomes unstable. This is what happens in chemical reaction. But in there they can react with more and can be more stable, but in this case, when it just goes because of light energy excitation mode, it immediately reverts back, gives out the energy, but some of the energy lost as heat in the process, and therefore the light energy that is now coming out has less energy and therefore longer wavelength. This is what is called a Stokes effect, because this was discovered by scientists called Stokes. And so what we see is, we illuminate an object with blue light, but what we see output is green light, because some energy in this process of excitation and reversion got lost as heat, and therefore light comes out, and this property has been utilized in fluorescence microscopy. Certain molecules by themselves, even biological molecules, have the property of fluorescence, but certain other molecules, organic and inorganic, they can combine with various molecules in our cells and give them fluorescence property. They can be chemically synthesized, they can be natural products, like quinacridine was one of the earlier natural products which are used as a fluorescence component, because it will bind specifically DNA, and therefore it was a chromosome fluorochrome. The quinacridine, the drug that is used for malaria treatment. Fluorescence filter cube, which will allow one wavelength of light to pass and illuminate the object. Illuminate now returns the wavelengths, the original incident light illumination, one particular wavelength, and the fluorescent wavelength. And what this filter cube will do is allow only particular wavelength that we want to reach our eyes. For example, this filter cube makes use of a very simple system, that this side is the light coming from illumination, from the source of illumination, for example, mercury light, completely white light. Now here is a filter which will allow only blue light of a certain wavelength to enter, all other wavelengths are blocked. Then in the center here is a dichroic mirror, which is very special kind of glass, which when light comes at this angle is completely reflected down. And this is in the optic axis with the objective, so that light, this particular wavelength now will be reflected to the objective and therefore on the object. The object generates fluorescence because of this particular wavelength that has certain molecule that will give fluorescence, and that fluorescent light will now travel up by internal reflection. This is what I am showing is in a typical upright fluorescence microscope. Similar thing will happen in an inverted microscope. And this here on the light that is going to reach our eyes or detector system, there is another filter which will not allow this wavelength to pass through, but will allow only the fluorescent light to pass through. For example, you have blue here and green here, red here, and green there and red here. So depending on what kind of fluorescence you are looking at, you bring in the particular fluorescence cube in the object view. And this is how it looks like, the same diagram as I shown you earlier, but this is where the filter cube is located, this filter cube. This side, this faces the light source, mercury lamp. Light comes in here, the dichroic mirror reflects it down to the object. Object now reflects the incident light or excitation light as well as the emission fluorescence light. Both the light waves are now traveling up again. Dichroic mirror in this angle is completely transparent. It's no more reflecting now. That's the property of dichroic mirror, that at one angle it is reflecting and another angle it's like an ordinary transparent glass. But then the filter here, top filter here, which we call barrier filter or emission filter, will allow only certain wavelength, which is the wavelength that is coming out as fluorescence. That only will reach, and so we will see only the red color, not the white eye. And that's the fluorescence microscopy it does. Same thing can be in an inverted microscope, where the objectives are under the stage. You can have Brightfield illumination, you can have fluorescence illumination, and same thing. These are typically useful for large objects, for cultured cells and so on. That's where one uses inverted microscope. So the fluorescence, what happens is, you can get like there are different fluorochromes, the various kinds of fluorochrome that can give you some natural molecule that bind with all proteins or certain specific proteins, or what most common use now is using antibodies. Antibodies tagged with specific fluorochrome, so that where the antibody will bind to the antigen, you will get that fluorescence property tagged to that. One can combine fluorescence and phase contrast. You can look at the live cell structure and also you can look at fluorescence. This needs some adjustment in illumination, brightness and diaphragm adjustment, but one can see beautiful phase contrast image as well as fluorescence image. Or one can combine DIC image, for example, this is a DIC image, and where a fluorescence is going on. For example, this is the nuclear area, this is something else, and this is where fluorescence is. So one can make these combinations of DIC fluorescence, phase contrast fluorescence, and so on and so forth. Or one can do immunostaining, RNA localization, DNA localization by using in situ hybridization. For example, this picture in top shows the polyethylene nucleus with this red is the specific RNA, such as omega RNA. Wherever it is located, we can use specific probe, and that only appears fluorescence. In this case, a particular protein, the HNRNP-A1 homolog, antibody using it, antibody against that we can find out on which chromosome this protein is present. And that allows us to look at, now of course what has happened is, now many of these proteins are tagged with GAP, so you can look at them live cells. We have lots of Drosophila stalks which have GAP tagged, and therefore you can look at in live, because GAP will fluoresce as it is, and you don't need to fix the cell, and you can follow the GAP fluorescence and you can see how the molecules are moving. And if you combine with DIC, you can see the more detailed structure from where to where it has moved. Now this is, I come to the last part. Are modern tools necessarily better? Do we get best image, best information using only modern tools? And I am sure each of you remember mitosis was discovered by Fleming in 1872, and these are drawings that Fleming had made in 1872, hand drawn. And these are one of the very fancy confocal microscope images of DNA stained with DAPI and microtubule stained with, now you can judge for yourself. These are parallel images, interphase nucleus, prophase, metaphase, more advanced metaphase, anaphase suppression begins, anaphase happening, telophase happens. Now you can see for yourself. Now these images are drawn by microscope like this. If we give you a microscope like this today, what will you do? You will resign and go. We can't work here. But think of this. And the reason I show you this is that this is where lies the importance, what you can observe, how you can observe, and what kind of perseverance you have. I'll give you more examples of this kind. For the polytene chromosomes, this line drawing was drawn by Bridges, same Bridges, C.B. Bridges, who discovered in Northern Junction, the great man. He had hand drawn each of these using a special device called camera lucida, whereby you fix that device on the eyepiece, and what you can see an image of the piece of paper lying on the table and the object. And so using that, with your hand you draw whatever you are seeing. All the old drawings that we see were done by camera lucida. There are no photographic there, no camera as such. It was a simple camera system that you can draw, and he drew each of these lines as he saw them. Must have seen thousands of preparation, and he drew all the polytene chromosome arms, which we still use as standard reference, and he drew about 5,004 lines on entire nucleus. People in 1970 thought, okay, we can take photographs and do it better. So this is the best kind of photograph that, now again, entire chromosome has been built up, and that again required thousands of photographs to be taken of each region, stitch them together to make a straight chromosome. More adventurous people tried electron microscopy, that we can take polytene chromosome squashes and section them. I've also tried it. It comes out beautiful, but it needs enormous patience to build up whole thing. Maria Source and Vico Source in Netherlands, and then later on more recently Zimulov in Russia had prepared these polytene chromosome maps at EM level. But what is interesting and eye-opener is, when you look at this, what I show you in this region, each of these bands, when you compare with what Bridges had drawn, EM could not discover a single extra band. When the level of resolution and an EM and light microscope is several orders of magnitude. Now one can wonder, did Bridges have EM eyes? He had eyes, and he has patience, and he has perseverance, and he could draw each one thousands of times. He would look at it, okay, this looks always like this, shape and size, exactly you see that them it is. And this is a tribute to the power of observation that Bridges and people of the earlier times had. Another example, I give you great embryologist and one of the first cell biologists, Theodore Boveri. Actually, his description of cancer in 1914, he published a paper, what is a cancer, in 1914, wrote a review kind of a thing. And everything that he predicted cancer is what we are discovering in molecular biology today. But these are his drawings. He was an embryologist looking at the nematode ascaris development, and these are again hand drawing. Though the scientists had to be good artists as well. Different shades of color to indicate various kinds of molecules and so on and so forth. They process each cell as it comes out. If we photograph this, we won't see the details, because then we will be photographing only one level, not all the levels. But by changing focus, you can see this. I mean, something confocal will do today, you will get 100 sections, and then you stitch them, you don't get all the details. And that's where the beauty of keen observation and sensitive observation, have eyes to look at beauty and look at the facts, is very critical. And I'll end with this statement, that the automated and increasingly powerful equipment and tools available for cell biology studies now allows us lots of precise in-depth studies. We can combine biochemical, biophysical, cytological, molecular, everything together. But we must not forsake our own analytical insights while exploiting the power of modern gadgets. Gadgets are there, but if our brain simply depends on what is seen on the screen, we are really not human beings, we are not researchers. We need to look at what is hidden in that information, in that image. So I'll stop there, and if you have any questions, I can take them now. Thanks.